It is a section 14.7, maximum and minimum values. In Calculus 1, you learned how to get those values for functions of a single variable. Let's see the recall. To find the absolute maximum and minimum values of a continuous function f defined on a closed interval ab, the first step is to find the values of f at the critical points of f. Secondly, you should find the values of f at endpoints. Among those values, the largest one is the absolute maximum value, and the smallest one is the absolute minimum. Also in Calculus 1, you learned the second derivative test for functions of single variable. F prime at c equals 0. That means c is a critical point, and at the point second derivative is positive, then f has a local minimum. Once the second derivative is negative, then f has a local maximum. In Calculus 1, I guess you used this example. F of x is x squared, and f prime, which is 2x. If we set it equals 0, then we can see x equals 0. That is c, a critical point. Now f double prime, which is 2. So at c, again, the value is 2, which is positive. If you draw the graph of the function y equal f of x, then at c, 0 is equal to 0, you can easily see that is a local minimum. In fact, this minimum is the absolute minimum of the function. Here we define local extrema the same way as for functions of one variable. F is a function of two variables, x and y. The function has a local minimum at point AB if f of xy is larger than or equal to f of AB. Here xy is chosen near around AB. At AB, f has a minimum value in surrounding area. Then we say that that is local minimum value. Once f of AB is locally maximum, then that is local maximum value. That is the definition. Now we consider the first derivative test for functions of two variables. If f has a local extremum, which means that either local maximum or local minimum at the point AB, then the first order partial derivatives exist. Okay, in fact, that's an assumption. Once derivative exists, then f sub x at the point must be 0, and also f sub y at the point must be 0. That means gradient of f at the point equals 0. So that is exactly a simple expansion of the first derivative test considered for functions of one variable. Here we have a self-study problem. Find the critical points of the function. That means you have to solve this problem. Gradient f equal 0. So in x derivative and y derivative, and you set them equal 0 and solve the equations, then you can find two critical points. Now we have the second derivative test. It is an expansion of the one for functions of one variable, but it is a little bit different. The second order partial derivatives of f are continuous around the point AB, and also we assume that the gradient of f at the point is 0, which means AB is a critical point. Now we define D is f sub xx, f sub yy, minus f sub xy squared, and evaluated at the point AB. We define D. We'll see the meaning of this quantity in here. In the beginning, D is positive, and f sub xx at the point is positive, then f at the point is a local minimum. This portion is the same as for functions of one variable. F sub xx is negative, then f at AB is a local maximum. But this one is true only when D is positive. Because a function has more than one direction, we need this condition. We'll see the meaning. D is negative, then f of AB is a saddle point. Let's see what D is. Yeah, first of all, once D is 0, then the test has no conclusion. No conclusion can be drawn from this test. Now, D is made in this way. D is determinant of f sub xx, f sub xy, f sub yx, f sub yy. This product, which is this one, that product, this is subtracted. Now, once second derivative, partial derivatives are continuous, then from Clairaut's theorem, we know that f sub xy and f sub yx are the same. So we can get this term. So this D is a determinant of the metric. This metric is called the Hessian metric of F, and determinant is called the Gaussian curvature. So D is the Gaussian curvature, which is the product of principal curvatures. So you may think in this way. The D is the product of curvatures, also product of eigenvalues of this metric. Now, curvature positive and curvature negative, and the two eigenvalues can be positive or negative. Once they have the same sign, then D must be positive. If they have different sign, then D must be negative. So here, D is positive means that in one direction, in principal direction, the curvature is positive, and the second, the principal direction, again positive, so that it can be local minimum. once one direction is negative, then the other direction is also negative, then again this is positive. In this case, it can be local maximum. We are using only f sub xx in this theorem, but it's the same as f sub yy have the same sign. Once this is positive, okay, this term is positive, and also if f sub xx is positive, then f sub yy must be also positive, so that this quantity can be positive. Once it is negative, then f sub yy must be also negative. That means f sub xx, f sub yy should have the same sign when d is positive. So even though we write down here only f sub xx is positive, in fact, this inequality implies that the other one, f sub yy, is also positive. The same way, f sub xx is negative, then also f sub yy must be negative. Okay? Okay. Find all extrema, local extrema of the function. Okay. We have to find first the critical points. So we start with the gradient of f. X derivative 4x cubed minus 4y. And y derivative is 4y cubed minus 4x equals 0. Then from here, divide by 4, and that is x cubed equal y, and y cubed equal x. We recheck this one. So here, cubed, and then x to the 9 equal y cubed. Y cubed is the same as x. That means now x to the 9 minus x equals 0. Then from here, x is common, so x to the 8 minus 1 equals 0. So we can conclude here x is 0 and 1 and minus 1. Then y must be, okay, x is 0, then y must be 0 by using this equation. X is 1, then again y is 1. X is minus 1, then again y is minus 1. So we have 3 points, 0, 0, 1, 1, minus 1, minus 1. Now we have to decide which one is local minimum or maximum, or which one is a saddle point. In order to do that, we may try to use the second derivative test. And we have to decide D first. In order to do that, okay, we need to get second derivatives. F sub xx, that is 12x squared. F sub yy, from f sub y, one more y derivative, which is 12y squared. Now f sub xy, for this x derivative, we apply y derivative, then that is minus 4, so that d is this two product, 144 x squared y squared, and minus that squared, which is 16. Now for 3 points, we have to decide the sign of this term. Okay, this is xy, so d at the point x is 0, y is 0, and then that must be minus 16. Now x is 1, y is 1, and then that one is 144 minus 16, which must be 128. Again, for x is minus 1, y is minus 1. Again, same value, 128. So at the point, it must be saddle point. At the point, it must be local minimum. Again, another local minimum. Right? Okay, let's see this figure. This is 1, 1 position, which is a local minimum. That is minus 1 position, another local minimum. This is 0, 0. And this direction, the curvature is positive, and along that direction, the curvature is negative. So that D is negative, and this is a saddle point. Okay? Find the shortest distance from the point 632 to the plane. You may try to find the answer by using formula you learned from high school. The formula is given in this way. Or now we may try to use the optimization technique. And now let's try to get the solution by using the formula. Okay, A. This formula, the point is now x0, y0, z0, and that is A. A is 2, B is 2, and okay, that is B is 2, and C, that is minus 1, that's A, B, C, and that is D. Okay, so capital D, the distance, shortest distance is now A, 2, x0 is 6, plus B is 2, and y0 is 3, and C is minus 1, and z0 is 2, and D is 2. Okay, divide by A squared, B squared, C squared. I'm sorry. A squared is 2 squared, B squared is 2 squared, C squared is 1 squared. So that must be 3. Now the numerator, we can cancel these two, and 12 plus 6 is 18 over 3. That is 6. So that the final answer must be 6. Now, if we try to use the optimization technique, then we can formulate it in this way. If we choose an arbitrary point on the plane x and y and z, then by using the Pythagorean theorem, from this point to that one can be formulated as a square root of that term. And we try to minimize so that we can decide x, y, z. But here, rather than square root of this term, we try to minimize d squared, so that distance squared will be this one. Okay. Oops, it is just a moment. Okay. Now, distance squared is given in this way, and we define this portion as f of xy. Now it has 3 variables. For z minus 2, if we move this into right side, because x, y, z are chosen from the plane, now x, y, z will satisfy this equation. And z minus 2 is same as 2x plus 2y. So this portion is replaced by 2x plus 2y. So finally, we try to minimize this term, and from the minimum value, take a square root to get the final answer. Okay? Okay, in order to do that, we have to use the derivative technique. First, we have to find the critical point. Okay, gradient of f. For that one, now x derivative is 2x minus 6, and it'll be 0. And for this one, plus 2 and 2x plus 2y, and x derivative we have to have here 2. How about y derivative? Twice of y minus 3 plus, now from here to 2x plus 2y times 2. We set it 0. Now we can cancel out this 2 divided by 2. Now that one, okay, this one will make 4x plus 4y plus x. So there are 5x plus 4y minus x will be moved to right side to be 6. Again, 4x plus 4y plus y. So the 4x plus 5y equals 3. Right? Okay. From this one, now to eliminate one variable, we may try to multiply 4 here, multiply 5 here. So that is 4, then 20x plus 16y, which is 24, 5, then there's 20x plus 25y equal 15. We subtract, then that'll be 0, minus 9y equal minus 9, which means that y equal minus 1. Once y equal minus 1, then it's minus 4, move the other side, then by adding 4 it becomes 10, which means that x equal 2. So we have a critical point, x is 2, y equal minus 1. So we have to measure f value, x is 2, y equal minus 1. Then, now from this one, x equal to then 4 squared plus x, y equal minus 1 minus 4 squared, which is again 4 squared. And then x equal 2, then 4, y is minus 1, is minus 2, so 2 squared. That is now 2 squared, which is 16, 32, 36. So that is same as the d squared, minimize the d squared. So the final answer d, the minimum value, is square root of 36, which is same as 6. So we have the same conclusion. Okay. Okay. Find the volume of the largest rectangular box in the first octant with 3 faces in the coordinate planes and 1 vertex on the plane. Okay, let's try to visualize the problem. Okay, there's x direction, there's y direction, that is z direction. For that one, once we try to get y and z are 0, then x must be 2. So here, intercept over there is 2. In y direction, okay, x and z are 0, then y must be 3 here. And in z direction, x and y are 0, then it's z-axis. At z, that must be 6. So if we try to get a triangle connecting this 3 point, then now the plane is the one including this triangle. Now we consider a rectangular box. Okay, so that will be made in this way here. Now, and oops, okay, that is there is a rectangular box, and here, like that. And okay, the 3 faces okay, in the coordinate planes. So the 1, 2, 3, the bottom one, and then this point is now the vertex is on the plane. Okay, so we want maximize the volume. Okay, we start with this is x, the point that is x, that is y, and that is z. Then the volume must be xyz. Of course, xyz is satisfying that equation because this point will be xyz. xyz are chosen from the plane. So eventually we have to maximize the problem f of v equal xyz and subject to this condition. And by using this condition, we may simplify the variable. Rather than 2 variables, rather than 3 variables, we change it into 2 variables, x and y, by using that equation. So we reach that one. V is given in this way. Now we have to maximize. In order to do that, we have to find the critical point. Once you can find a critical point, and if it is a single critical point, then you don't have to use second derivative test. That'll produce the maximum value. Okay. Okay. So we try to get the critical point. Okay. For that one, gradient of v. X derivative, we have to use the product rule. Okay, that is first x derivative, then there's y, and 6 minus 3x minus 2y, and here, and again x derivative here, then that will be okay minus 3 and xy, right? And secondly, from this one, and y derivative, then there will be x, that is 6 minus 3x minus 2y, and y derivative then, okay, is minus 2, so it is xy. We have to solve these equations. Okay. Now, to maximize the volume, xy cannot be 0. One of them is 0. Then the volume must be 0. So that we may assume xy are non-zero. So we may here cancel y here, because this equals 0 and y is a factor, so we can cancel out. And also we can cancel here x factor. Then from this one, now that is, okay, first one is 6 minus 6x, 3x minus 3x, minus 2y equals 0. From second one, 6 minus, that is minus 2y, so that minus 3x, and minus 4y equal 0, right? So, okay, let's rewrite this one. We move these terms to right side, then that is 6x plus 2y, 6x plus 2y equals 6. And that is 3x plus 4y equal 6. Okay. We'll try to multiply 2 for this second equation. Now, rather than that one, we consider 6x plus 8y equal 12. So rather than this one, we consider that one. Then subtraction will make minus 6y equal minus 6. Okay, that means here y equal 1. Once y is 1, then from this one, any equation here, y equal 1, then 6 minus 2, which is 4, 6x equals 4, so y is now 2 over 3, right? And once again, oops, that is x, right? X, y equal 1, and y equal 1, x is 2 over 3, then that'll be 2, that'll be 2, so the z must be 2. Okay, so we found all values required. So the volume, maximum volume is xyz, along with the quantities, and 2 over 3, y is 1, z is 2, so that final answer must be 4 over 3. Okay. Okay. Now, absolute extrema. This one is also a simple expansion for the one used for functions of one variable. F is continuous on a closed and bounded set in the plane, and then F attains an absolute minimum value and absolute maximum value at some point. Okay, so it's the expansion of that one. For example, y equal fx, that is defined on a closed interval a to b. Then you can find always absolute maximum and absolute minimum from a to b. Once a continuous function y equal fx is given, then it may have go up and down like that. Then you may try to get here the critical value, and here the critical value and edge values. Among these one, largest one is absolute maximum, smallest one is absolute minimum. So it is exactly the same way we can find absolute maximum and absolute minimum for functions of two variables. To find this absolute extrema, And the first step is try to find the critical points and at the and the corresponding critical values. And secondly, now we try to find the extreme values along the boundary, and among them the largest one is absolute maximum and smallest one is absolute minimum. So it is the strategy is really almost the same as for functions of one variable. Okay, let's try to find the absolute extrema of the function on the region. Okay, first we try to find critical points and corresponding values. Okay, start with gradient of f, x derivative, that is 2x, now minus 2y. Okay, that is background noise. My cat is playing with a toy ball. Okay, I'm sorry about that. Okay, now y derivative, which is here minus 2x. Okay, that'll be 0. Okay, and plus 2. Right? Okay. If we set 0, then from second equation, we know that that is x is 1. From first equation, x is y, so that again, y must be 1. So we found 1, 1. At 1, 1, if x is 1, y is 1, then 1, here, minus 2, plus 2, right? So that the value at the point is this 1, 1 position is 1 minus 2 plus 2. So that f is now 1 here. Okay, so we found the critical value. Now, along boundary, we have to decide maximum and minimum. Okay, first, okay, that is the first side, and that is the second side, that is the third side, and that is the final, the fourth side. Okay, for first side, now y value is 0. Of course, this is 0 and 3 in y direction, 0 and 2. Okay. Y equals 0. Then f becomes y equals 0. Then f becomes x squared. That means there's no critical value along the line, and here we have, okay, let's try to use red pen. The f value must be here 0, and at the end x equal 3, so here f must be 9, right? How about that one? And that is x equal 3, then f becomes, okay, from this one, 9 minus 6y and plus 2y. So that is 9 minus 4y. Okay, so it's linearly decreasing. So y becomes 3, y becomes 2, then the value must be 1 here. So along the boundary, the extreme values are here or that one, so that f is 1 here. Now it's linearly along that direction is decreasing, right? Now third one, there's y equal 2. Okay, the boundary is y equal 2. Y equal 2, then f becomes here x squared minus 4x and plus 4, which is same as now x minus 2 squared. So it is quadratic. At 2, f becomes 0, and at 0, f becomes 4. So we found the critical values along the boundary. And now final one, that's x equals 0. Then f becomes, from over there, x equals 0, then f becomes 2y. Okay. And the last boundary is linearly changing, so there is no critical value in mid around here. So we found every possible extreme values. Here is 0, 1, 9, 1, 4. Among them, smallest one is 0, and largest one is 9. So minimum is 9, a minimum is 0, maximum is 9. Okay? Okay, that's the end of section. Thank you.